So good evening, one and all. I am profoundly delighted to take an opportunity to introduce the guest of honor for today's session, Dr. Rohit Mehra. Dr. Rohit Mehra is presently working as an associate professor in the Department of Physics at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. Mr. Mehra has published more than 170 SCI research papers in different international journals of repute and has delivered invited talks in various countries, including the USA, UK, Canada, Japan, Egypt, France, Thailand, etc., and served as a member of various organizing committees of international conferences of repute. He has supervised 17 PhD research scholars and more than 50 PG dissertation, and presently 4 research scholars are pursuing their PhD under his supervision. Presently, he is an active reviewer for many international and national journals in the field of radiation dosimetry. He is also a collaborator with a working group at NIRS, Japan, for inter-comparison activities for radon and thoron measurements. He has published 3 books and 3 book chapters in the field of radiation measurements, which are extensively referred to be as baseline study in the field of radiation measurements. He has worked as principal investigator of various R&D projects and fetched the funds for approximately more than 2 crores from various funding agencies like BRNS, CSIR, DSD, etc. He is also a member of the editorial board of 3 international journals in the field of radiation physics and reviewer for more than 40 international journals of repute in the field of radiation physics. Presently, he is Vice President of Nuclear Track Society of India, BARC, Mumbai, and Honorary Vice President of International Accreditation Organization, Houston, USA. Apart from his academic responsibilities, he has served as various administrative positions at NIT Jalandhar, including Registrar NIT Jalandhar, Associate Dean Student Welfare, Associate Dean Research and Consultancy, Associate Dean Faculty Welfare, Professor in Charge Legal Cell, and Head Department of Physics. So we are delighted in welcoming you, sir. Now the session is over to you, sir. Thank you, sir. Namaste, sir.
Namaste. Thank you. Thank you. Thanks for the nice introduction.
Yes, sir.
Yeah. And thanks to the organizers and especially the Ishwar College for giving me an opportunity to share my experiences with you people on the topic of environmental radioactivity, where we are today we will be dealing with the biological effects of environmental radiation. And I'm thankful and honored that Dr. Krishnamurthy has given me this opportunity, and I hope that this talk for the next 2 hour or 1.5 hour or more will be informative to you, especially for those people who are working in the area of environmental radiation monitoring. So to begin with, we have divided this talk into the 2 portions. Firstly, we will be dealing with the first category, biological effects, and then the second category, that how to go for the analysis. So I will try to sum up the inputs given by me by giving you an opportunity to ask the questions also at the end of this session, so that at least if you have some queries, you can always ask, and you can even raise your queries on the chat box or during the talk if you are interested. So you could also write down in the chat box, and I request the organizers to note down the questions if any are there, and then we could discuss those questions also.
Okay,
Let me share my screen. Visible or not? I think still no.
Sir, screen is not set, sir.
Yeah. I think now it's visible.
Yes, sir. Now it's visible, sir.
So let me make it full screen. Are the slides moving?
Yes, sir. It's moving, sir.
Yeah. So we'll be dealing with the biological effects of radiation, and under this category, I will be telling you what are the different types of radiation, how those are impacting our day-to-day life, and then we will be proceeding to the measurements of those type of radiation. So starting with the outline of my talk. So the basic idea of radioactivity, and then we will discuss what are the routes of exposures. Then we will discuss how the interaction of gamma rays take place with the matter, because that is the role where the physics plays a very important role. That how the gammas interact with the metal, and then sample preparations for the measurement, and finally the introduction to the gamma ray detector, and finally radium equivalent and the final calculations we will be proceeding. Now, if you say the types of radiation, so basically we are dealing with two types of radiations. One is the ionizing, and second one is the non-ionizing radiation. And if you see the figure, it starts from a very low energy to the radio waves, and to the very high energy cosmic rays. They have been spread out. And most of the time, the ionizing as well as the non-ionizing radiation, there are different groups of researchers who are working on ionizing radiation. There are different group of researchers who are working on the non-ionizing radiation. So both plays a very important role and impact on your human body. So like in our group, we will be mostly concentrating on the ionizing radiation, as we are dealing with the direct ionization methods and even indirect ionization method. And most of the time we will be dealing with the alpha, beta, gamma, and X-rays. And the next one is neutron. So why we have categorized the neutrons under this category? The reason is, though neutrons are not directly radioactive in nature, but if you allow the neutrons to strike some of the materials, they allow alpha, beta, and gamma to come out. So that is why the neutrons, the study of neutrons is also very important for the ionizing component. But in terms of non-ionizing radiations, we are dealing with the radio waves, UV, visible, then IR, infrared, then microwave. So you know it's a long range which is going on. So in our group, in our lab, we are dealing with these alpha, beta, and gammas only. And as I think most of you are teachers, no? So very basic information which every teacher should know as a teacher of physics. There is a very big confusion to the students that they cannot differentiate between gamma and X-ray. So generally, so many times this question have been asked in the interviews from so many students, from so many experts to the students who are appearing in the interviews, that what is the basic difference between alpha, gamma, and X-ray. So generally, you might be aware of the fact that basic difference is the origin difference. The X-rays are coming out of the electronic transition, but the gammas, they are generally coming out of the nuclear transition. So nuclear transition means once the proton changes into neutron, neutron changes into proton, and then within the nucleus some transitions take place. So basically, we are dealing with the gamma. That is the basic difference between gammas and X-rays. Otherwise, rest of the things, frequency, wavelength, everything is similar. So you cannot differentiate on the basis of those things. Now, just to summarize what we have discussed, that we can further categorize radiations into two categories. That is the particle radiation and then high energy electromagnetic waves. And similarly, on the basis of your non-ionizing radiations, you are having so many low energy electromagnetic waves and then ultrasounds also. Now, we at NIT Jalandhar basically are corresponding only or dealing only with the ionizing component, not the non-ionizing component. Of course, this study is also very important, especially nowadays when there is a big study is going on for studying the harmful effects of especially the mobile phones or mobile towers. So in that case, you are dealing with the non-ionizing component, and which is very important also. Moving. Yeah. So just to see that what is the actual basic difference between alpha, beta, gamma, and X-rays. If you see, this picture gives you a very clear-cut idea. Is the slide visible? Alpha, beta, gamma?
Yes, sir, it's visible, sir.
Yeah. So the basic picture, if you see, there is an alpha which can be stopped by a thin sheet of paper, and beta can penetrate through it, and then a thin sheet of metal of aluminium can stop the beta. And then gammas and X-rays, then they can be stopped by a thick lead or a steel plate. And finally, neutrons, they can be stopped by water, paraffin, or concrete. So if by seeing this picture, if somebody asks that which is more dangerous, what element is more dangerous, or alpha, beta, or gamma? So by seeing this picture, one could easily guess, or one could easily answer that, of course, neutrons are more dangerous, then gammas are dangerous, X-rays are dangerous, but alphas are very less. But as a physicist, if you say, so the answer is wrong. So by seeing the picture, maybe the answer seems to be very okay because you are wearing a shirt or a suit or a sari and you are being attacked with the alpha rays or alpha particles, and those clothes will stop those alpha particles. They will not penetrate those clothes and affect your body. But in terms of physics, if you say, the ionization power of alpha is very high. So what is the meaning of ionization power in this point? That if suppose there is a 2 MeV alpha or 2 MeV gamma is there, both are having similar energy, 2 MeV. Now, if the 2 MeV alpha or 2 MeV gamma strikes a person, so which one is more dangerous? By seeing the picture, one could answer that, of course, 2 MeV gamma will be more dangerous because it can penetrate within my body and it can have an effect. But now talk in terms of physics, the ionization power, the alpha has the highest ionization power, means it can ionize the skin instead of the gamma, which is having a similar energy of 2 MeV, but that energy is being transferred across all the tissues and the organs. So if you just calculate the radiological effect, so 2 MeV at a skin is more dangerous as compared to the 2 MeV across whole body. So that is why the study of alpha is very important in terms of ionizing radiation. And the alpha is the only, you could say, particle which is responsible for causing most of the radiation damage. So even over gammas or X-rays. So that is why the study of alpha particles or alpha emitting sources is very important. And most of the time, once you talk about the radiation measurement or health hazard effects of radiation, so most of the times you will be dealing with those sources who are alpha emitting sources. And we are concentrating mostly on those sources like radon, radium, boron. So all are alpha emitting sources, and most of the detectors which have been prepared,
ஆனா
they are
என்ன இது
based
இப்போ
upon
ஆஃப்லைன் மோடு வந்து போகணும் நம்ம
most.
இன்னும் போனோம்னா அப்புறம் எதுக்கு வேஸ்ட் அட்டெண்ட் பண்ணிட்டு இருக்கோம் 2 days 1 week
So because this type of problem happens during the online discussion, somebody start talking without muting his mic. So it's a common nowadays. Like we are having some students who are talking during the classes, so we have to understand it. Similarly, we could understand during
Yes,
our
sir.
discussion if somebody keeps his mic on a non-mute mode, unmute mode, and start talking. But anyways, so most of the time when we discuss about the radiation, especially those ionizing radiations, we are mostly concentrated upon the alpha sources. Now, there is a question asked sometimes that why we are having a different units for the radioactivity, why we are confusing our scientific community with the use of different types of radioactive units. Sometimes we call it as becquerel, sometimes we call it as a gray, sometimes we call it as a civet. So what type of unit we should use in which environment? So the best answer I have tried to give it with this picture. So like if you want to calculate the disintegrations per second, that is the amount of radioactivity which is there. So the basic terminology which you could use is by seeing this apple falling from a tree, that how many apples are being fallen on the earth. So we could say it is the number of disintegrations per second, and the best unit is the becquerel. But suppose there is a passenger or a passerby is coming and he had a nap beneath this tree. Now, on his body, some of the apples will fall, which have been shown in a green color. So out of this falling apples, only green color apples will have an impact on his body. So only absorbed dose is important for a person once he is under the influence of radioactivity. So once we talk in terms of absorbed doses, we talk in terms of gray, like the green apple. That is the number of apples that hit the sleeper that can be compared to absorbed dose. Now, once we have absorbed, what will be the effect on our body? That is also important because my organs behave in a different manner. So that is the important task for the researchers now to calculate the gonadal doses. Like if I have been exposed to the radiation, it's not possible that Krishnamurti and myself will have a same impact. The reason is my body mass index will be different and his body mass index will be different. My exposure time will be different, his exposure time will be different. So that is also important, that we have to keep the calculations of exposure time, we have to keep the calculation of body mass indexes. Even different organs behave in a different manner. So that is why the ICRP is nowadays most of the time is concentrating on the ICRP biokinetic modeling. Like for different organs, you can calculate the different doses or impacts. And once we calculate the different doses or impacts on the different body components or parts, what is the effect that is measured in terms of civet. Now, this table will give you a very basic idea that if you have been exposed to different sources of radiations, and if your effective dose impact actually is of the order of say 50 to 100 millisieverts, it can change your blood chemistry. We all who are the radiation workers who are working in the field of radiation measurements, we know that 2.4 or 2.3 millisievert is an average annual dose which every person receives across the world. That is a worldwide average due to the natural sources of radiation. Even though we have been not exposed to any external or artificial source of radiation, still we receive 2.4 millisieverts per year. If you undergo some treatment like CT scans or X-rays, that dose may increase. But on an average, due to the natural sources, due to the environment, we have been exposed to 2.4 millisieverts. Maybe in the southern areas where the more monazite sands are available, the exposure may be to a little bit on a higher side as compared to the areas where there is lesser thorium or radium or potassium. But on an average worldwide, we could take it as a 2.4 millisieverts. And out of this 2.4 millisieverts, we know that 55% contribution is only due to one natural source, that is radon. So radon studies are very important, especially once you start for the health hazard effects of radiation. So nobody could escape from the radon because it is a noble and inert gas, and it is a decay product of radium. So once radon 222 decays by emitting some alpha particles, it creates polonium. And then after polonium 218, once it further decays by emitting an alpha particle to generate polonium isotope of 214, then that alpha is very much responsible because it has an energy of the order of 6 to 7 MeV. So that energy is capable. That energy is capable to cause some effects on our bodies. So as it is a gas, which is present across whole of the atmosphere, we could inhale it. So once we inhale it, and once we inhale something which is emitting the alpha particles, and we know that alpha has the highest ionization power, so that energy will be liberated on the internal lining of our lungs. And if our exposure is very high, beyond some permissible limit, so that energy could accumulate such an effect that our internal lining could suffer, which is the major cause of lung cancer after cigarette smoking. So that is why the study of radon in terms of health hazard effects is very important, because radon is present everywhere. Even though right now where we are sitting, you are sitting in different place, I am sitting in northern part of India at different place, but we are under the impact of radon because we are under the impact of natural air which is having radon in it. So that exposure may be different for you, and that exposure may be different from me, depending upon my ventilation condition, my building materials. So that is why the study is not restricted to the physics or the environmental scientists. It is restricted to the civil engineers. It is not restricted to the even architects. All have to sit together, because our exposure is to be calculated based upon the natural combination of exposure from all sources. If we are using granite in our houses, that is having more exposure. If we are having sandstone, that is having a different type of exposure. If we are having a cement which is containing more fly ash component, that is having a different exposure. So depending upon the architectural point of view, building materials point of view, even the civil engineers point of view, exposure may different. Now this is a chart which I will be discussing. It is of a high level of exposure. So if high levels of exposures of 50 to 100 millisievert occurs, it can change our blood chemistry, and we could feel the nausea in the terms of 500 millisieverts, and impact could be felt within hours. So for a case of even chemotherapy, once you go for chemotherapy, some of the radiation exposure occurs to you of the order of say 700 to 700 millisieverts. So within weeks, you could measure the impact. You could have hair losses, vomiting, diarrhea. And then if you go on having increased exposure, that effect could even lead to the death. This is a basic chart which gives you an idea that how the radiation exposure can lead to different types of health effects. This last column indicates that within how much time those effects will be measured. Now, like I was discussing, that is 2.4 millisievert is an average natural exposure to every human being. So we have categorized it into two different types of radiation exposure sources. Like one are the natural sources, another are the artificial sources. Like I told you that if you have undergone some X-rays or if you have undergone some CT scans, you have been again exposed, and you have some consumer products which are having more radioactive exposure, like granite. Even the black granite is also very highly radioactive in nature nowadays. In terms, still the impact should be in the permissible limit. I'm not saying that if you are using a black granite, you are very much exposed to the radiation. That may be within the permissible limit, but the nutshell effect, the annual accumulation will be more in your case as compared to the person who is not using that black granite. So this is how the combination of natural as well as the artificial sources and the percentage we have given. The sources Anskia report 2008. Now these are our routes of exposure, that how we could inhale or how we could ingest or how it could enter to our body. So there are different routes, and it also depends, like I have already told you, that it also depends that how much time I spent there. Like the tree which I have shown you, the radioactive tree, which is having apple falling from the tree, that is number of disintegrations are there. But if I am not going to that environment, that radiation exposure will not impact me. So for what time I am going under that environment, when I am going under that environment, and how much time I spent there, that makes a sense, not only the number of disintegration. So if some area is radioactive in nature, that doesn't make hue and cry for everyone which is not available in that area. So it depends upon the exposure time also, it depends upon the environment on which you have been exposed. Then there are some external exposures, there are some internal exposures. So depending upon exposures, impact will be different. Like in the beginning of my talk, I have told you that suppose alpha source is there and you have been exposed to the alpha source, you need not to worry, because you are wearing some clothes which can stop that alpha. So your body will not be impacted. But if you have inhaled that alpha source, now the impact will be different, because now that energy which that alpha will liberate, if your energy cannot penetrate your body from outside to inside, then again from inside to outside it cannot penetrate. So it will liberate whole of its energy to the internal linings of your lungs. So then you have been more exposed. So you have to understand that what type of exposure has occurred, whether it is only external exposure or whether it is only the internal exposure. Depending upon that, radiation suggests it calculate that how much exposure has been given to me, and based upon that, he has to choose the different types of materials. And the best way to keep the exposure minimum is ALARA, which is a very common term. ALARA, keep it as low as reasonably achievable. ALARA, as low as reasonably achievable, because sometimes during the natural exposure we don't have any control. If we are residing at a place which is having more natural radioactive contamination, the only thing which you could use is either to leave the place, which is practically not possible, or to keep ALARA. ALARA means you should keep it as low as reasonably achievable. You should increase your distance from the radiation sources. You should keep your exposure time to the minimum value, and then you should have the best ventilation condition where you could keep it to the reduced value. So that is very important, because as a radiation worker, our job is not only to make the people aware that this is the radiation source, but also to make them aware that and tell them, even though one has been exposed, still, if it is beyond permissible limits, it's a cause of concern. If it is within the permissible limits, we should not create hue and cry, because our version will create a different impact on the human being. So that is why it is very important for the persons who are working on the field of radiation sources that while publishing your studies, you should be very careful. Don't use a very big term. It could create cancer to the human body, because radiation not always, of course, exposure creates some damage, but it is not always cancer. So you should be very clear in your studies, and that how much exposure is there. Now, if you talk in terms of interaction, because as a physics teacher or a student, one should know that how the gamma rays are interacting with the matter, because without knowing them, you cannot go for gamma ray spectroscopy. And especially for the radiation assessments in soil, we go for a gamma ray spectroscopic techniques where we measure the radium, thorium, and potassium in soil, and then finally decide that how this exposure takes place and what are the values which we calculate. So, there are basically very uh, well-known facts about the gamma's interaction with the matter, and three famous laws: photoelectric effect, Compton effect, and the pair production, which are very important. So that is, yeah, I think we need not to go into the detail of those things, no? So, we will be. I think there is one query in the chat box also. No, it is only good evening to all. So, its interaction with the gamma rays depends upon either we are working with the photoelectric effect, or we are working with the Compton effect, or we are working with the pair production. So I have mentioned all the three things. I'm not going into the detail of those things, that what is pair production, what is Compton effect, and what is your pair production. But photoelectric effect, uh, again, which as a physics teacher or a physics student, one should know that the probability of getting electrons ejected from the K shell is maximum in the photoelectric effect as compared to the KLMN. Though the binding energy of K shell is very high, but still the probability of getting the K electrons ejected is very high. The details you could study from some of the nuclear physics books, or if somebody wants to ask, we could answer in a different session. But that is also very important, because the teachers who are teaching the photoelectric effect, the Compton effect, and the pair production, I would request them that study those things in a very detailed manner, and then discuss the thing. And the probability for K shell is very high as compared to LMN, though the binding energy of the K is the highest. Then I would come to the basic idea that how we could measure the radioactive contamination or content in our soil samples. So I have tried to summarize all of the things into a single slide. That firstly we get a soil, uh, preferably this is a hole dug up by the auger. Preferably we want to use natural soil, and we get the soil from the depth of around 0.75 or 1 meter depth, so that we could get the natural soil. So that the effect of the artificial manures or some other contaminated materials which are present on the upper layer of soil, they are not there. Then the soil is crushed into fine powder and air dried for 24 hours at a temperature of less than 40 degrees Celsius. Then this is an oven where we dry our samples for at least 3 hours for 110 degrees Celsius. And then the samples are steamed by using a sieve of approximately 150 micrometer scientific sieve. Then the sample are packed and they are being weighed and then packed in some PVC container. Now, a very important thing is, like, this geometry of the PVC container is very important because every detector has a different type of a geometry. So for our detector, which we are using, the ATAL sodium iodide detector, this container is of a particular geometry. It's a pearl pet packet or having a capacity of around 150 grams. So previously we are having a detector which is having a capacity of around 250 grams, but this is a detector where the best geometry is with the 150 grams, and then they are packed and weighed and packed, and we wait for at least 6 to 8 weeks before the analysis, so that the radioactive equilibrium occurs in the sample, and finally the samples are ready for their installation in the detector. And then this is a detector, so we install the samples within this detector by opening this opening. We could rotate it, and then this is our detector, which is of the size 63 millimeter to 63 millimeter, having efficiency of less than 20%, but resolution of 7% for cesium and 661 keV with activity of 9 kilobecquerel. So then energy detections of this detector is of the order of 50 keV to 3 MeV, and minimum detectable activity for radium, thorium, and potassium is 3, 3, and 30 becquerel per kg. If your activity concentration is less than 3 becquerel per kg of radium and thorium, it will not detect it. So that is the minimum. And the time for analysis is 1800 seconds. Previously, we were also using the HPG, which is a highly, which is having very high resolution, but it was having a neutron nitrogen, liquid nitrogen chamber along with that, because that detector requires so much cooling. So we have discarded the detector now, and we are using only this sodium iodide detector, because though its resolution is not so high as compared to HPG, but of course it is good one for within a portable range we could measure. Then this is the diagram which is actually showing that there is a detector and there is a source which we have placed. There is a lead field across whole of the detector, and finally it goes to some amplifiers and multi-channel analyzers, and we plot some of the curves. So based upon the activity concentration. And we know that what are the energy ranges for different materials. So depending upon the energy of radium, thorium, and potassium, we calculate the area under those peaks and finally calculate the activity concentration. Now, this instrument is being calibrated with the cesium source, cesium 137, and this is the source which is available in our lab. So we have calibrated it, and these are again, this is Rg uranium, this is for potassium, this is for thorium. So Rg uranium, thorium, and potassium. So we have an energy range of 186 to 21 to 2614 keV of energy, and reported efficiency is uh, less than 20%. Less than 20% doesn't mean the detector is having efficiency of less than 20%. The only thing is the gammas which could cross, which could measure, they are interacting with the materials and thus producing scintillation. So not 100% we could detect. So we will measure the peaks only. And this is a figure which shows that for potassium, for radium, for thorium, we are using different energies. So we are using 146 keV of energy for potassium. If there is a peak across this energy, we say potassium is present. And similarly for radium 226, we are using 186 and 609 keV of peak. Then for even lead, we are using some of the energy. Helium for 270, 727 keV. So these are different energies of bismuth, actinium, and different standards which we are using, and we are calculating the area under those peaks. Nowadays, everything is being done with the help of software, but previously when we were pursuing our PhD, we calculate a curve fitting technique, we apply the curve fitting techniques and finally calculate the area under those peaks, and then we calculate the activity concentration. And this is how the activity is being measured, that we calculate the counts per second, then multiply it with 100 and 100 and divide it with the branching intensity and efficiency. Like for every different energy, the branching intensity is different and the efficiency is different. So we are having manuals along with our detectors, which is giving us an idea that what is the branching intensity linked with a particular energy and what is the efficiency of the detector for that particular energy. So if I am measuring thorium, my efficiency will be different. If I am measuring radium, my efficiency will be different. My branching intensity will be different. So for every different energy, my same detector is having different branching intensity and different efficiency. So one couldn't say that my detector is this much efficient. It is efficient for a particular energy. For a particular energy, it may be 40% efficient. For another energy, it may be 70% efficient. So that 20% means minimum 20% is efficient for everyone. Now this is how we place the sample, how we insert the sample by rotating it. So it creates a 4-pi geometry. So because on the upper side there is also a detector, so it creates a 4-pi geometry where we place the sample after the 1.5 month filling, and then this detector detects it. And finally we get the activity concentration along with some values. So these are the results shown by some of the samples. The weight is approximately 150 grams in our case. Like I've already told you previously, we were using 250 grams, but now we are using 150 grams. So sometimes some of the researchers send their samples in a sealed container to us, but that sealed container is not having a similar size as compared to the container which we are using. So we have to again open up the samples again to seal in our containers and then again wait for 1.5 hours so that the radioactive equilibrium again occurs. So that is why I generally suggest the researchers who are using our facility that once you send the samples, please send in the containers which actually we are using. So our container has a different geometry, and if your container is having a different geometry, results will vary because geometry plays a very important role. Then after measuring the radium, thorium, and potassium concentration, what we do that we calculate each thing in terms of radium and we call it as a radium equivalent. Now, there is a very famous equation which is well known to the persons who are working in this field, that radium equivalent is given by the concentration of radium plus 1.43 into concentration of thorium plus 0.07 into concentration of potassium. Now, from where this term 1.43 and 0.07 comes, it comes from this term like 370 becquerel per kg of, I'm sorry with the mistakes in using superscripts, it is per kg. It is 370 becquerel per kg of radium produces the same gamma dose as it is produced by 259 becquerel per kg of thorium. If you divide 370 with 259, you will get 1.43. So that is why to convert thorium into radium, we are using a factor 1.43 because the same gamma doses we are taking into consideration. So 370 becquerel per kg of radium produces the same gamma dose as produced by the 259 becquerel per kg of thorium. So if we divide 370 with the 259, we will get a value of 1.43, which has been placed as a multiplication factor. And similarly, 4810 becquerel per kg of potassium produces the same gamma dose. So if you divide 370 with the 4810, you will get a factor of 0.07, which is here. Now, from where this 370 comes, it comes from OECD reference. That is acceptable limit. So if your exposure is beyond 370 becquerel per kg, then your hazard index will be more than unity. So means you are hazardous. So your exposure is hazardous. So to keep it under unity, OECD in 1979 has pointed out that it is 370 becquerel per kg, the radiation exposure from natural sources. On the basis of that, we have calculated the hazard index. Like if you place the activity of radium 370, it will be 1 plus something. So that is more than unity. We have to keep it under unity. So these are the formulas which give you an idea that we should keep it within 370 range, we should keep thorium within 259 range, we should keep the potassium within 4810 range. So that is why these values are there. And for a room, this is exposure hazard index without doors and windows. If your ventilation conditions are very good, then you could reach to the double value. So you see, by just increasing the ventilation conditions, 370 comes out to be 740. 259 comes out to be 580, and 4810 comes out to be 9620. So that means by heading only with the increased ventilation conditions, with the similar environment, your exposure reduces to the half value. And in terms of internal exposure, there are some lesser values because internally, if you are having some building materials in that transfer, so those are the lesser values because radium has an important role to play in their case. So internal exposure only radium value is reduced to half. That is 185. And based upon our activities, we could also calculate the dose. So these are the formulas which indicate that how the internal and the outdoor doses are being calculated by measuring the activity concentration of radium, thorium, and potassium. And then from the doses, we could calculate the effective equivalent doses in terms of millisieverts, that is the organ doses which have been referred here as the indoor absorbed dose rate, then dose conversion factor, and indoor occupancy factor, and finally for annual, how many hours you have been exposed. So for whole year, if you have been exposed, we have calculated the value of AED. So the basic terminology used or equations used have been referred from the different sources of Anscare, OED, and ICRP. And finally, by measuring the activity concentration, you could always convert your doses into effective equivalent doses, that is on the organ doses calculations. Similarly, there is a definition of the working level month, like if you have been exposed to the radiation, how much exposure occurs to you, that depends upon how much time you spend. So any radiation worker or any person who have been exposed, so it is calculated in terms of working level month. So that is a unit to express the accumulated human exposure to the radiation. Similarly, from the ICRP calculations, this working level is equivalent to 2.08 into 10 raised to power joules per meter cube. And like I have already told you that I was telling you about the branching intensity and efficiency in my previous equations, when we were calculating the counts per second and then we converting those counts per second into the activity concentration. So why the branching intensity and efficiency plays a very important, it comes from a very important parameter that you have to calculate the R, that is decay rate, specific activity, which is available. So depending upon a particular specific activity, how much exposure occurs, you should calculate it. Branching intensity is a fraction of decay that is accompanied by the emission of a specific energy of gamma ray. So, for example, the most intense gamma ray emitted by uranium has an energy of 185.7 keV and a branching intensity of 54%. So it means uranium-235 decays by alpha particle emission with a half-life of this much years. So it means that emission rate of 7.98 into 10 raised to power 8, 4, only 54%, because branching intensity is 50%, 4%.
And then we can keep the question sessions at the end of the second session, sir.
Okay, thank you. Then I will join in 10 minutes.
Yes, sir. Right now the time is 8 p.m., sir. We can schedule by 8:10, sir.
Okay, thank you.
All participants, please be in the meeting so that you can join after 10 minutes.
Yeah. So we have discussed various impacts of radiations, and then we have followed with the sample preparation techniques for the estimation of uranium, thorium, and potassium, and in the soil samples, which is very important in terms of your radiation assessment. In this talk, we will keep you aware about the different exposure routes, and then we will discuss that how the measurement of radon is being done with the help of the detectors which have been nowadays designed by the BARC, and how those detectors plays a very important role in the estimation of radon detection. Because in our previous talk, I have already told you that you have been exposed to the natural radiations, and radon is one of the major contributor in that. So in this portion, we will be discussing the different ideas about the exposure, and then this is the radiation protection quantities, like how quantified intake by ingestion or inhalation could impact you, and what are the different models, biokinetic and dosimetric models. They are responsible for calculations of the quantified exposure due to the inhalation or injections. Then we calculate the mean absorbed doses in terms of organs or issues. And then based upon the radiation weighing factors of different organs, we calculate the equivalent doses to the organs. Then once we calculate the equivalent doses to the organs, then based upon the tissue weighing factors, we calculate the effective doses. So our study starts from the quantified assessments of injections and inhalation doses, and then finally effective doses, which takes the input from the different biokinetic and dosimetric models, then radiation weighing factors of different organs, and then the tissue weighing factors of different organs. And finally, we calculate the effective dose. And we are most of the time concentrating on the effective dose instead of the basic measurement techniques. So these are the important criterias, or you could say that how this radon and the thuron, they and their progeny, means daughter products from the air, could impact us. So the basic idea I've already discussed with you people, why the estimation of radon is important, because it is the largest contributor and it is the decay product of radium and thorium. Radon and thoron both, they are the decay products of 226 radium and 224 thorium. And then as they are the inert gases, so their study is very important. And once you inhale those inert gases, it could enter into your lungs, and then after inhalation, once they enter our lungs, they releases their alphas by decaying within their half-life of around 3.4 days, and then those alphas are responsible for causing different effects. So radon is the second leading cause after the cigarette smoking for the lung cancer. So the source is the WHO. There are three main isotopes: radon 222, radon 219, and radon 220, out of which this radon 222 is having a half-life of the order of 3.82 days. And thoron has a half-life of the order of 56 seconds, that is 55.6 seconds. So they all are coming from the decay chains of uranium 238, 235, and thorium. And then from the source term, we calculate the emanation and the pores, then exhalation, and then atmosphere. So everything is responsible. So entry into the building by the gas phase molecular diffusions or additive transport of air, they could enter our bodies. So you could see that there is a house which we have prepared. And finally, those radon and thoron who are entering, then those radon and thorons who are entering, they are decaying to release the polonium isotopes. And then from the polonium, we have been exposed, and finally there are some attached and there are some unattached fractions, and finally attached as well as unattached fractions play their important role, and finally they deposit on our internal lining. So depositions and ventilations. So radon, being the chemically inert, exhaled out mostly short-lived decay product are polonium 218, then polonium lead 214, then bismuth 214, then lead 212, and then bismuth 212. So they attach to our respiratory tract tissues and finally irradiating them with the alpha particles and inducing the lung cancer. So out of this, unattached has a size of less than 10 nanometers, and attached fractions has a size of the order of 10 to 100 nanometers. So as you know, based upon the size, like if you see some of the coarse particles, if you filter out some of the materials or fluor from a sieve, so the particles which are of a bigger size, they stick to the sieve. So similarly, they are the attached fractions which are of higher sizes. So which can pass through that sieve, they are called unattached fractions, which are of very lesser sizes. So similar cases, like in this case, a very small size, we call them the unattached fractions of radon, and the bigger size as compared to 10 nanometers, we call it as attached fractions. Then another contributor is the uranium, which we will be measuring, or I will be discussing. And like apart from the radon, we measure the uranium also, of course, radium, thorium, potassium in soil. But another contribution is from the uranium in groundwater. So just to study the chemistry behind the uranium, that it is a natural lithophilic element and has a valence states of 4 plus and 6 plus, that is tetravalent and hexavalent, which are very important for the study. Of course, it has more than hexavalent and tetravalent, that is 2 plus and 3 plus, 5 plus states. This tetravalent is insoluble, but hexavalent state of uranium is soluble in water. So once a thing is soluble in water, suppose uranium is present in the soil, and if it is present in its hexavalent state, so any water source which is passing through that soil, any river or any pond or any other water source which is passing through that soil, so that soluble component, hexavalent component, will mix with it, and that it will travel from its source to some of the faraway places. So sometimes uranium in groundwater, we estimate the uranium concentration in groundwater, and the sources are at very far off places. And especially in northern India, where we are mostly dependent upon for our irrigation purposes on the rivers. So if the source is in Himachal and a Ganga or a Yamuna starts from that area where we are having some higher uranium contamination levels, and it reaches even to the Hooghly area in West Bengal. So still, by passing through from that particular area, which is highly contaminated, that hexavalent compound will also travel. So by estimating the groundwater concentrations, we have to take care of the geology of that area also, that how this means, what is the basic origin of this uranium contamination. So that is why the study of hexavalent compounds are very important. So there are three naturally occurring isotopes of uranium, which we know, that uranium-238 and 235 and 234. So out of which, in soil or in most of the time in our water samples, we measure the uranium-238, and the contamination level of 235 is also measured. But 235 is enriched uranium, which is used as a nuclear fuel. And of course, if you could extract 235 out of 238, so you could make a good source of uranium as a nuclear fuel also. So then it enters the groundwater aquifers as a result of natural geochemical processes like mineral dissolutions and desorptions and absorptions of uranium from the mineral surfaces. Then anthropogenic contribution means if some mines or nuclear facilities are available in that particular area, then again some anthropogenic contributions are very important and responsible. And sometimes the fertilizers are also responsible. So nowadays there is a big boom on the projects which have been given by the BRC people, that they are calling some projects related to the anthropogenic contributions, like the enhanced uranium concentration level due to the use of excess fertilizers. So that that is the area where you could apply and you could get the projects nowadays. Then, of course, human beings are exposed to the uranium while inhalation of gaseous and aerosol uranium, drinking groundwater. So, which is the largest contributor for the uranium exposure, because nearly 40% contribution is only due to the drinking purposes. So, of course, food ingestion and dermal contacts, they are also responsible, but most of the time we are having the contribution from the groundwater. Then another important parameter is to measure the radioactive and chemotoxin like heavy metals also, because they are also responsible for causing different radiation exposure to our bodies, and biological impacts are there, and our kidney, liver and bones, they are prone to the uranium deposits and other heavy elements. So we in our lab, we are the only lab, especially in rather nowadays, we could say most of the time in India, who are working on the biokinetic hair compartment model, and we are calculating the canodal doses. Of course, it's not so cumbersome work which we are doing, but our work is being appreciated by even IISc Bangalore, and there is a one center in IISc Bangalore where we are having some academic collaborations, and BRC we are having some academic collaborations, and even NIRS Japan we are having academic collaborations where our lab is working for the intercomparison of different detectors also. So now, another important thing which I was discussing is the estimation of heavy metals, and there are different heavy metals in which we are interested, depending from starting from arsenic to copper, from cadmium, then lead, and because those trace elements and their toxicity also plays a very important role, so their study is also very important. So most of the time they are concentrated in terms of group 3 to 16 in the periodic tables. And of course, their study is important. Now, this is the basic technique which I will be sharing with you people, the basic detector, which is a very basic common detector, which we call as a pinhole cup dosimeter, which has been prepared by the Sahu et al. In 2013, and before the pinhole cup dosimeters, we were using the detectors which are not so much efficient, and some of the basic limitations of a bare mode and other dosimeter cups have been removed in this dosimeter, and it is a detector of this shape, which is of different compartments. These black rings, which you could see, they are the places from where you could open up this detector. And there are different compartments. So these are the 4 holes which have been provided in the compartment partition, which is responsible for allowing the radon to enter from lower compartment to the upper compartment. This is a gas entry. If you see the bigger figure, this is a gas entry, which or the progeny, which is entering from the environment to the hanged detector. It enters to the first compartment, which is having a dimensions of the order of 4.5 centimeter to 7 centimeter of diameter. So 7 centimeter of diameter. And this compartment is known as a radon plus thoron compartment, because most of the time in this compartment, the effect of thoron as well as the radon will be measured, because thoron is very volatile in nature, having very lesser half-lives. So it does not penetrate across this compartment and enters to the second compartment through the 4 holes which have been provided. Only radon could penetrate through these holes and enter into the upper compartment, as it is having higher half-life also. So nearly 97% cutoff take place, and this rest upper compartment contains only radon component. So this is a single phase gas entry of 0.56 micrometer glass fiber filter paper is placed, and then this filter paper allows only the gas to enter. So it filter out the progeny combinations and other combinations. So two identical cylinder chambers which are been separated, and 4-pin configuration which I have already explained. There are two detectors which have been placed, one at the downward side of the partition of first and second compartment, and one on the ceiling of the second compartment, means on the upper side of the second compartment. So this detector detects basically both radon as well as the thoron, and the upper detector detects only the radon, because only radon is allowed to penetrate through this detector or through this compartment. Then we calculate the concentration depending upon the branching intensity and the track recording. So these are the formulas which have been given in the literature by so many researchers also, and could read down the paper of Sahu et al. To find out that depending upon the exposure time, day, or geometry of this detector, finally the concentration is calculated. And there is another detector which have been introduced by the BRC, which we call as a deposition-based progeny sensors. Now, these are the types of detectors where we call it as a DRPS and DTPS, that is direct radon and direct thoron progeny sensors, which are not only detecting radon and thoron, but they are detecting their progeny. Progeny means daughter products. So one we call as DRPS, that is direct radon progeny. Another we call it as a DTPS, that is direct thoron progeny. Because radon decays 222, decays by emitting some alpha particle and creates 2 polonium 218, and then which further decays by emitting an alpha particle of the order of polonium 214, and that alpha has energy of the order of 7.69 m. Or not?
Yes, sir. Yes, sir. This was there, sir.
So means I have explained the working. I think it's clear now.
Yes, sir.
So then we are also measuring the progenies of radon as well as the thoron. So where we are having different detectors, which we call it as a deposition-based progeny sensors. As we know, a radon 222 decays by emitting an alpha and comes out to be 218 polonium, and then further decays to 214 polonium, which emits an alpha of the order of 7.69 MeV. And our LR115 or sometimes CR39, some of the peoples were using, but we are using the type 2 LR115 detector, which is the cellulose nitrate film, that is sensitivity is of the order of 4.5 to 5 MeV. So if any sensitivity of the order of 4.7 or 4.5 MeV means if any energy of the order of 4.5 or 5 MeV comes to this detector, it will be sensitive for that and it could create a track. So I'm not going into the detail how the track formation is occurring, because that is known by most of the radiation workers, and Walker, Fletcher, and Price have explained it in a very detailed, elaborate manner. That is, the traces of their release of energy is called a track. So for the energy range of the order of 4.5 MeV or 4.7 MeV, it creates a track. Now, another is the thoron, which is 220, and if 2 alphas are emitted out, it comes out to be 212 polonium. by 220. Firstly, alpha meted out, then it will be 216 and then 212. And there is an alpha which is having energy of the order of 8.78 MeV. Now, these two energies are very important for us because they are the highest energies emitted during this decay process and their progeny, and it is very important to measure their contribution. The previously what we were doing, we were assuming that for 90 days our detectors have been exposed, so these progenies are also contributing because it is a similar energy, high energy. So we are assuming this energy as energy of the radon itself, but it is actually due to the progeny. So now we could differentiate between the parent and the daughters. So that is why the study is very important. Now, if you see, there is one energy of the order of 7.69 MeV and there is another energy of the order of 8.78 MeV. Now, our detector is sensitive for the energy range of 4.7 or 4.8 MeV. Now, to make this energy of the order of 4.5 or 4.7 MeV, we require some of the absorbers. So we have placed absorbers. If you see this figure, to reduce this, there will be a thinner absorber is required because this is a lesser energy as compared to 8.78. So we use a 37 micrometer absorber for case of 7.69 MeV and 50 micrometer absorber for 8.78 MeV. And there is a big task which has been performed by the BRC team for selecting the absorber thickness, because it is not only within a day that you could find out that this is the absorber thickness. Dr. Maya and Dr. Mishra has spent a lot of time in estimating the thickness of those absorbers, and they have calculated so many theoretical calculations also, and finally reached to a conclusion that we could use 50 micrometer and 37 micrometer absorbers, mylar films, which is responsible for causing the energy released from polonium 214 and 212 into the sensitivity range of these LR detectors. Now, again, it is very important that commercially we are not getting a film of 37 micrometer. Commercially available film is having a thickness of the order of 25 micrometer. And if you combine two layers of those mylar film, you could have a 50 micrometer absorber. But it is very difficult to have a 12 micrometer, means you cannot split that 25 micrometer aluminized mylar film into the half, and you could get a 37 micrometer film. For again, some calculations were performed by their team, and they have found that this upper layer of unexposed LR115, that is having a thickness of the order of 12 micrometer, and their absorption coefficients and capacities are very similar to the aluminized mylar. And we remove the upper layer of unexposed LR115, that is which is new LR115, which has been not been exposed, and then we put that layer across this. So it acts as a 12 micrometer plus 25 as a 37 micrometer, and finally that is being used. Then there is a wire mesh capped detectors are also that, or like previous case, we have placed a wire mesh over the detectors, because I have already told you that we could differentiate between fine attached and unattached fraction also. The thickness which are attached means that is some bigger sizes, they attach to the mesh, and the unattached can pass through it. So we can differentiate between coarse and fine particles also, and we can calculate the attached as well as unattached detectors. So they are called the wire mesh capped DTPS and DRPS, because that wire mesh is capable to differentiate between fine and coarse particles. So we generally hang these particles simultaneously. So this is one detector, this is DTPS and DRPS, there is wire mesh DTPS and DRPS, and we place all the three sets together to get the best information and follow some protocols of measurement. The best protocols have been given by the BRC, that we should keep our detectors at least 20 centimeter away from all surfaces so that we don't get the direct exposure from the building materials. We could only get the exposures from the air around our detectors, and these detectors are being hanged for a time period of 3 months to 4 months, depending upon the availability of different seasons in the areas. And then after this, we remove or retrieve our detectors and repeat the calculations for a whole of the year for selecting different seasons. And finally, after removal from the detector, these LR115s are chemically aged using a 2.4 normal sodium hydroxide solution at a temperature of 60 degree for 90 minutes and without any stirring. Then the films are dried and must be peeled off a cellulose acetate base, and the registered alpha tracks are counted using some track counters like spark counter, and then background track density due to the detector's shelf life and during handling must be subtracted. So what we are doing, we are exposing the detectors to generate some latent tracks. Then we perform some chemical etching techniques to make them visualize, and then finally evaluate, count the number of tracks with the help of spark count. And depending upon the tracks, depending upon the exposure time, we calculate the activity concentration. So this is how we could calculate the equilibrium factor also, depending upon the activity concentrations for the attached plus unattached, and then the concentration of thoron, because we are having all the three types of components, DTPS, wire mesh DTPS, and the concentration from the pinhole cup dosimeters. So we tried to calculate the equilibrium factor, and this equilibrium factor for our case, which we have conducted, ranges from 0.27 to 0.61 or 0.47 is an average value. And worldwide, OnScare has also given a similar type of average value. So we could say that our detectors are very capable enough to reach out to the average values equivalent to the OnScare, and new standards have been set, because now we are not only measuring only effective equivalent concentration, but we are separating the progeny from the parents. So which actually we were confusing in our previous researches, that we were assuming the progeny as a parent itself. So actually it is a contribution from the polonium, not from the radon. So these are the unattached fractions which we calculate, and of course from radon inhalation doses we are calculating from the concentrations. We are using the dose conversion factor and finally calculating the inhalation doses. Then annual effective doses we are calculating from the same concentration for the radon as well as for the case of thoron. Of course, we are also working in our area where we are working on a new type of radon smart dew. Previously, we were using some CAN techniques which were having some limitations and measuring the exhalation rates from the soil samples. Now there is a smart radon dew which is capable of estimation for the mass exhalation rates from radon and thoron itself. Using that detector, we are measuring by using PMT photomultiplier tubes. We are calculating. So this was the cases related to the radon. Most of the time we are working on the radon and thoron concentration in air as well as exhalation rates in soil. And then we are also working on for the biological effects, you should calculate the uranium in groundwater, which I have already told you that is a 40% contribution or the exposure is from the groundwater itself, from the uranium. So that is why the study of uranium is very important. And there we are using a LED fluorimeter, which is a very capable instrument. Of course, we can use AAS as well as ICP-MS. In our institute, we are having all these facilities. We are having AAS in our lab. We are having ICP-MS in our lab, but still the most reliable technique, which for uranium estimation we are using, is the LED fluorimeter. So where LED fluorimeter, it's a Quantalase manufactured LED fluorimeter, actual picture of that fluorimeter, where we are using a reference material from the ICP-MS, which is manufactured by the AQ standard, and analytical range is of the order of 0.5 to 1000 ppb microgram per liter. Means it can measure uranium contamination level of the order of 0.5 microgram per liter to 1000 microgram per liter in the samples. Then measurement time is very small, that is nearly 1 second. Within seconds you could get results. Then we use a fluoran, which converts various complexes into a single form. Then elimination of fluorescence of optical matter is being used with the help of optical filters and proper gating of the PMT. And this is the electronics behind the instrument. And then the calibration mode is 6 ml sample plus 0.6 ml buffer. So that is a calibrated mode where we do the calibrations before starting the readings. Some uranium standards we have to procure from the vendors or from the market, and then finally make the buffer solutions for 10 ppb, 100 ppb, and we perform different readings for 10 ppb, 100 ppb, 1000 ppb, and by making different readings with the different buffer solutions, your calibrations comes out to be an effective range. And then after measuring the uranium concentration, we apply the biokinetic modeling to our measured values. And this is the hair compartment model of ICRP, which is being shown to you, that how our blood plasma is responsible for calculating the different doses to our skeleton, liver, then injection, through injection, the stomach. You see, it's a two-way communication. Means from liver it goes to the plasma, from the plasma it goes to the liver. Similarly, from the plasma it goes to the skeleton, from the skeleton it goes to the limit. And there is one addition as compared to the ordinary biokinetic model in the hair compartment model, that we are using the hair also. Means our hair, natural hair on the body, they are also responsible for a contribution, and nearly 32% contribution is only due to the hairs. So not only the soft tissues or the urine or the livers or the other values which are responsible, most of the time hair are also responsible. So we are using a hair compartment model, and we are the only lab in India basically who are working on it. So these are the values, that is the maximum contamination level given by different agencies, where the WHO and US EPA has given it is of the order of 30 microgram per liter. It's a ppb, microgram per liter. So in India, the AERB has raised the limits to the 60 microgram per limit, because our mass to activity conversion is 40 microgram per becquerel of natural uranium, average daily intake of 2 liter by adult, and exposure have been calculated on the basis of 365 days per year. So our doses are a little bit on a different size as compared to the WHO. So AERB will be in a better position to answer that why some very high doses are being recommended as compared to WHO. But ANSCARE in 2000 has recommended a very low level of dose, that is 9 microgram per liter, and ICRP has recommended it to 1.9 microgram per liter, that is ppb, 1.9 ppb. Then uranium retention in different human and different organs, we also calculated. And average uranium retention in whole body after chronic intake of uranium via drinking water for 60 years is 7.77 microgram. So this much of uranium is present with an average life of 60 years. So this is how your soft tissues, how kidneys, how TBCs, CBVs are responsible for uranium retention. And these all are the basic informations which are available from the ICRP's website also. And we have tried to calculate the time-dependent uranium retention in different organs also. This is the time in terms of days. And you could see that for the case of CBV, the retention is very high. And in case of the livers and in case of your kidneys, the retentions are comparatively lesser. So in totality, for a time period of 60 years, this exposure comes out to be in terms of 7.7 micrograms. Like this 7.77 microgram. This is a combination of all the things. Similarly, you could calculate the different results, and we have tried to calculate for our present study in this area. Especially in this study was conducted in Solan district of Himachal Pradesh. That how much uranium retention is there in the kidney and the liver. And for our studies, the liver retention was of the order of 0.32 and skeleton retention was of the order of 31.45, which is very similar to the studies conducted by one of our student in Rajasthan, which is Jaku et al., who is presently in Dubna, Russia, performing his postdoctorate fellowship. The kidney retentions in the case of Rajasthan was of the order of 0.45, because that depends upon the intake of water also, because Rajasthan is a little bit more humid and they take more concentration of water, and their eating habits are such that they take more intake of chilies also, and similarly more water intake is there also. So retention is also a little bit higher. Then, of course, excretion range via different pathway. So from here to feces and urine, we have calculated it from the biokinetic modeling, that average amount of uranium excreted from the body per day, 0.018 microgram is through hair, and then feces from 0.036, and urine is 0.018 microgram. So you could see that the most of the excretion is equivalent excretion is from the hair as well as from the urine. So here studies plays a very important role, because it performs a different type of studies nowadays. Previously, we were ignoring it, but hair compartment model takes into consideration the excretion from hair. So that is why hair compartment model plays a very important role. Then, of course, this is the distribution of total effective doses to the different organs in the human body, and we have tried to make a calculation of lungs, muscles, ovaries, pancreas, spleen, red marrow skins, testes, uterus. So for every different organs, we have tried to calculate the annual effective doses from the intake of uranium. So for the brain, for the breast, bones and surfaces, and the kidneys, because direct ingestion from the water, kidneys plays a very important role. So they are generally having higher concentrations or higher effective ingestion doses. Then heavy metal concentrations is also very important. I have already told you that we are having different facilities of AAS as well as ICP-MS. So physical chemical parameters we also try to calculate, and we measure the pH, electrical conductivity, and TDS values. And this is a figure which is showing the AAS, which is available in my lab. And we try to calculate the annual daily doses to the humans from the different heavy metal concentration. And finally, we calculate the dermal absorbed doses based upon the average daily doses. And then from the dermal doses, we calculate how we are being exposed. So this basically finishes my talk, and discussion is now open. So if anybody want to ask any questions, you could ask that how we are working, or what type of pathways which are responsible. So your biological effects are based upon the concentration of heavy metals, concentration of uraniums, concentration of radon, concentration of radium, thorium, and potassium. So I have tried to summarize all the things, like we are measuring in terms of soil, we are measuring in terms of soil, radium, thorium, potassium. In terms of air, we are measuring radon, thorium, and their progeny. In terms of water, we are measuring heavy metals and uranium contamination. And finally, we are combining all the effects. So this is how we could proceed for a good PhD work also. Like if we do these type of analysis simultaneously, so your work is always supportive. One research is supportive with the another research. So the best results you could generate. So now the talk is open for the discussion. If anyone or any attendee want to ask anything.
Participants can put forward the questions to Dr. Mehra. He'll be much satisfied and be pleased to answer your questions. It's over to the participants.
Participants are available, or they are busy in their dinner actually.
Yes, most probably this is the late evening, so members are available. Let's see the things. Let's go for the questions, the queries.
Krishnamurthy sir.
Yes, sir. If participants hesitate to ask the questions, you can type in the chat box so that we can read it. This is an interaction session which undergoes evaluation also. Thank you, madam. You can put forward the question. Otherwise, you can type in the chat box so that we can read it out.
So I think Krishnamurthy, maybe you could take the feedback from them during the later sessions.
Yes, sir.
In the morning sessions when they will be highly energetic also.
Yes, yes, sir. And
So
I got a personal question, sir.
yeah,
When we undergo radionuclide detection for any materials, will
yeah,
it harm our skin?
yeah.
That was one question put forward personally.
Means when we get a radioactive exposure from some of the materials,
Yes, any material. Suppose we are detecting a material, will be harmful for the skin?
definitely some harm will be there, because I've already told you that if it is emitting some alphas, you are directly exposed to some alpha sources. They have the highest ionization power, but it's not always you could say that harm will be visible harm, because accumulation will happen to your some of the tissues, because our tissues generally, once they even have some exposure and they are torn up, after some days they are again regrown. So our exposure is not so continuous that we can feel that harm while detecting the samples. But of course, harm will be always there.
Yes,
It's
sir.
not possible that you are not exposed. You are exposed, but our soil samples and water samples, they are not so much highly radioactive contaminated. So in most of the India, the parts, the radioactive contamination level is within the permissible limits. There are few areas where we are having very high level of exposure, but that is mostly in the case of uranium contamination in water. In soil and air, we are still within a very limited scope, or within the permissible remit. Like in Iraq or Iran, there is a Ramsar area which is very highly radioactive. So still the people are living in that Ramsar area in Iran. So the contamination level is there as compared to different other regions, but still our body has is prone to that contamination. So it depends upon the inhabitants of that particular area. Sometimes due to the inhabitation or from the very long processes, their genetical deformation has taken place in such a fashion that they are not so much sensitive as compared to other people.
So one more the question they have asked, sir. Uh, what is the life duration of a radio detector?
A radio detector.
Yes, sir. They have
So
not mentioned which one. Generally, radio detector.
like LR115, which we are using for the radon detection, the life means once the detector is exposed, its life is over. So if for a case of a sodium iodide detector, ultimately the scintillator material is responsible for detecting. But after few years, you have to again recalibrate it. That is why generally the calibrations are being done after 2 months or 3 months or 4 months, that we want that our detector is capable enough to calculate the values. So that is why the calibrations are required every time. Means if it is a particular detector like LR115, once it is exposed, it is over. For a sodium iodide detector, it can work for years, but that depends that every time you have to recalibrate it. You have to adjust the peak values.
Yes. Okay. So one more question, sir. Are uranium deposit regions available in our country? This was the question asked by some.
Yeah, of course, the uranium deposit regions are available. Jaduguda mines is there. So that is why I have already told you in the beginning that we are thermal based country, and once you are having coal intake from the Jharkhand region where Jaria or mines are there. So they are adjoining to the Jaduguda mines, and those areas which are adjoining to the Jaduguda mines, if we are having some water sources traveling from those mines or those geological parameters, hexavalent compound could mix up. So that uranium 6 plus could mix up, and it could have its origin from the Jaduguda, but its exposure to somewhere else where that water source is traveling. So similarly, in the mine areas, even from the coal at the very deepen areas, we could have high levels of uranium contamination. In north region, there are some Tosham hills in the Bhiwani area which are granitic in origin. In south, there are some areas, high background radiation areas, which we call as a high granitic region. So there are some uranium deposits. Commercially available uranium deposits are different as compared to the naturally available uranium deposit. Jaduguda is a commercially available uranium source. So there are even some geological sources which are available, which are not commercially so much viable, but still their exposure is on a very higher side.
So one more question was put, sir. If thorium concentration is higher, will it cause cancer effects when we live in such regions for generations?
I've already told you that maybe thorium concentration is higher, but if it is within the permissible limits of 259 becquerel per kg, so still the external hazard index is less than unity. So we have to take the equivalent concentration of radium, thorium, as well as the potassium. We have to measure whether within it is within the permissible limits, because our recommended limits are 370 becquerel per kg for case of radium. So in case of thorium, it is 259 becquerel per kg. So if your concentration comes out to be more than 259 becquerel per kg, then your exposure is on the higher side. So but in most of the, even in certain areas which is having a little bit higher values of thorium, still it is very lesser values. We are not having a thorium concentration more than 60 to 70 becquerel per kg of in those particular areas even.
Any other questions, participants? Rather sending me personally, you can type in the chat box. Yeah, there's one question in the chat box, sir.
Yeah, Andhra and Telangana have uranium rich in India, whether it is an information or a question. I have already told you that there are so many areas. Geologically, there are so many areas. Yeah, of course, it is information only. Like Jaduguda is the highest concentration in Jaduguda uranium mines are there. So, like in northern region, I have told you the Sham hills are there. In southern Telangana and Andhra, they are having a high granitic, because most of the time your area in Telangana and your Andhra, that is a granitic rocks, because they have been generated from the lava. So, of course, contamination level will be on a little bit higher side.
So one more question was asked, sir. Why the coastal regions of our southern part of India is highly radionuclide regions compared to the north side?
Actually, that particular geology is important, because how those pathars were created and how those plateaus were created, because they are having high concentration of thorium even in the sand beaches. Monazite rocks are there, so that monazite is also responsible for a high concentration.
Yes, participants. Any more questions?
Whether radiation causes cancer? Of course, it causes cancer. I've already told you its exposure within the permissible limits is not so much dangerous, but if it is beyond some permissible limits, it definitely causes cancer. Even the natural radon which is present, once you inhale it, so if exposure is more than the permissible limits, so it can cause cancer. It can cause you the lung cancer, and it is the second largest contributor after cigarette smoking for the lung cancer.
Yes, participants, still more questions? Any other questions? You can just ask, sir. If there are no questions, shall we conclude, sir?
Yeah, of course.
Yeah. Thank you very much, sir, for this wonderful session towards this late evening. We began our session at exactly at 7 o'clock and we are carrying on till now. It is around 9:15 now, and still you are energetic and yes, and you are answering plenty of questions. You are interacted much and provided much valuable information about such radiation and radioactive materials and the process in biological effects. So how it has been affecting the biological parameters, okay, all effects, and many other participants are still messaging that it was a very useful and informative session. And thanks for your wonderful input, sir, and for interaction also. Thank you, sir.
Thank you. Thank you. Thank you.
Thank you very much, sir.
Thank you, Professor.